Today we are continuing on with 9.2b with our arithmetic sequencing. Or the arithmetic series. So here as I want to reiterate again, the arithmetic series or the arithmetic sequencings are linear and they have a constant rate of change. So let's say today we're going to talk about finding the sums, right? The sums of the arithmetic sequencing. And let's say we were given a scenario. We want to find the sum of the first 60 positive odd integers. So here we have to think about this logically, right? Let's think about this logically. Well, odd integers are like 1, then 3, then 5, then 7, and then 9. But then if you think about 60, right within the first 1 through 10, we have 5. 1, 2, 3, 4. So then to get all the way up to 60, our sequence goes all the way up, not to 120, but close to 120, right? Because if we had 120, it'd be close to 60. So it'd be one less. The last one would be 119. And if we also think about this logically, if we paired the numbers before 119, right? If we had 1 plus 3 plus 5 plus 7 plus 9 and we had 119. Before 119 we'd have 117. Before that we'd have 115, and before that we would have 113, etc. If I were to take the first if I were to cut this in half, right? If I were to cut the sequence in half, and I took the first half and I laid it with the second half on opposite ends, I noticed that if I did 119 plus 1, that's 120. And then if I did 117 plus 3, that also gives me 120. And 115 plus 5, that gives me 120. So I recognize that half of it, if you cut it in half and you add the sums on the opposite ends together, the sums are going to be the same. It's going to be the same sum numbers. So then if I took all that, right? If I took all that, I know that there are 60 positive integers. So if I took 120, right, and I added there was 30 of them. That gives me, so if I took 120 and there was 30 of them, right, I added it by 30 times, so then I just multiply by 30. That gives me 3,600. Or we can also use the formula, which pretty much says the same thing, where we can say, the number of integers that we're going to add. So this is assuming we're skipping integers, and this applies for both even and odds. And then we want to multiply the first value, a sub 1, plus the very last value, which is a sub n, and then we divide that by 2, in which our case we have 60 integers. Our first value should be 1. Our last value should be 119, and we divide that by 2, which is the same thing as 3600. Let me check here, double check my math just to make sure, and it is 3600. Both ways will give me the same answer, but this is the formula that you could use to get the sum quickly without having to add each integer one by one, without having to add 1 plus 3 plus 5 plus 7 plus 9, go all the way up to 119, because that's onerous and it's a lot, it's too much. But this is the logic that brings us there, right? And from that logic, this is the formula. The next thing is, what if we want to find a partial sum? So now I want to add all the numbers in a sequence, and we want to, of a arithmetic sequence, and we want to find the partial sum of that. So the formula there is S of n equals n times a sub 1 plus a sub n, all divided by 2, or we can say n divided by 2 multiply a sub 1 plus a sub n. So let's give this a whirl. So let's say we have 0, 0, -7, -14, -21, and my n value equals 20. So there's 20 integers here. First things first, I need to find a sub 1. Well, a sub 1 is my very first number, so that's 0. That then leaves having to find a sub n. Well, we do recall a sub n equals a sub 1 plus n minus 1 times d. Our d is how much it changes each time. Well, here from 0 to -7, well, that drops to -7, and it keeps going down -7 each time. So my d is -7. So I'm going to plug this in to find a sub n. So a sub n equals 0 plus 20 minus 1, that's 19 times -7. Here, plug that into our calculator. This, so 19 times -7 is negative 133. From there, we want to plug this into our original formula. So our original formula will give us the partial sum of this particular arithmetic sequence. So S of n is what? 20 times 0 minus 133. Divide that by 2. Let's see here. 133 times 20. Divide that by 2. My full sequence should then equal negative 1,330. One last example. Let's say we are given a summation written like this. We'll say this n equals 1 all the way up to 100, and we have -6n plus 30. Well, this isn't so bad. We can always find a sub with our formula. Just rewrite our formula again. A sub n equals n divided by 2 a sub 1 plus a sub n. So we can find all the values, right? Our n is 100 here, right? Because we're going from 1 to 100 is our n value. My a sub 1 is, we'll plug in 1 into our value. So a sub 1 must equal -6 plus 30, which is 24. Ace of n then equals negative 600 plus 30. Can you take 100, plug that into times negative 6 plus 30? So that gives me negative 570. So now we have ace of 1, and we have n. Plug that into our formula for our partial sum. So this becomes 100 divided by 2 times 24 minus 570. Punch this into, add this all together, times it by 100, divided by 2, and I get negative 27,300 for the partial sum of n equals 1 to 100.